Okay, first off, I just want to say, no, it's been a while since I've posted a video. I've been working on some other projects here. And also, I know this video is not going to be what I was working on in the past. Working on the transformer from scratch. I will get back to that, but yeah, while I've been working on other projects, I've been able to intermittently look at some stuff and do some vibe coding with anti-gravity. But basically, what today's video is about is looking at a few different pretty sweet things. There's this paper here, Clifford net, and a couple things that I've added it to, played around with. Let's see. First of all, yeah, Clifford net. This paper, you should definitely check it out. I have not even read the whole thing. Definitely still need to. But it's kind of a different system than doing self-attention. It is made for vision models, but my experiments, the one I'm going to show is going to be actually with a text model. But yeah, so I can read this here. Kind of a replacement for attention that they say works very well. It's okay, so Clifford geometric product is what it's based off of, which is the inner product plus this, what they call a exterior wedge product. Inner product basically is when you're doing the query and key, multiplying those two together, it's basically like an inner product. Seeing where one token is matched with another, like how much they work together. I don't know. And then this wedge product is supposed to be, I believe it is more. First of all, yeah, sorry. I will say that I do not fully understand. I did use anti-gravity to build this, so I'm still working on the understanding. But just thought I'd throw some stuff out here. But yeah, the wedge product is, if I understand this right, essentially they talk about it how it, let's see, it's when you a change in the context makes a change, how a change in the context actually changes the direction of the vector. So like you have each token is a vector, and it basically checks, okay, if we change the context, how much does it change that token vector? And that's what that wedge product does, I believe. Yeah, definitely read through the paper. You'll get a better understanding. But yeah, they use it for vision transformer, which I've done a thing with that, but what I'm going to show is it with an LLM, autoregressive. So that would be this original Clifford net. Okay, so we start with the benchmark that I always use, BPE Carpathy. We're using the Tiny Shakespeare dataset. These are the parameters using for this. Vocab size of 400. Okay, it's 400 on each. Just this one's 500. Okay, so take that into account. But we've got a few different checking the training loss and then the output. So the standard BPE with these parameters made almost 900,000 parameters, and this is the loss. Gets down to 2.7 for the training and the validation 3.05. And you can see it's coming into sounding like words. Some of these are actual, like seem like actual words, and then D is not. And then compare against Clifford Net, which we have, it's almost 1 million. So both of these are a little bit bigger. I should have adjusted for that. Let's see. And also this has a vocab size of 500, I'm just now realizing. So, which would, let's see, I think that actually increases, I think it slightly increases the loss with more tokens, but it also makes the training better. So 2.79 and 3.2 versus 2.70, 3.05. So it works pretty close, like very well for what it is. There's a lot of code, so I'm not going to go through all of it right now. Once I have a better understanding, I can, and if anybody wants, I can actually go through the models line by line, show how it's coded up. But what it does, okay, so there's the Clifford interaction, which will be the way it does this. It shifts the context. So here's the forward. So Z1 is it has a state, like a global state versus the local context or global context. I won't go into that, but let's say local context and a state, which the state is just the input that goes through a linear layer. There's this diff mode, which C ends up being like, okay, so it says discrete Laplacian, but it's the local context minus the global state. So it basically shows like, what's the difference, like kind of a gradient of the state versus the local context. That's what it uses during training. It also has an absolute, which would just be the context. There's these shifts, which I was saying how a change in context, the outer wedge product figures out how the vector changes with a change in the context. So that's what these shifts are. These shifts are changing the context by, let's see, there's that. Okay, so that's the default, but there's an actual shifts by, so shift by 1, 2, and 4. So the wedge is the state, the global state, basically the latent state, I guess you could say, times the shifted minus the shifted context by the shifted global state. And that's they say is an efficient way of calculating that. And then here's the inner product. Uses an activation function on it afterwards, which is the CLU, whatever you call that. Let's see. The other thing I wanted to talk about is, okay, to get the local context, they use, so we create what's called a causal conv1d. We'll go show that. Just a convolution with the stuff shifted. So that way let's see. That way future tokens don't get used here. So this way it only uses past tokens. But yeah, it uses convolution. So instead of a full self-attention, everything looking at everything, it is just looking at, it's using like a global state of everything, which is just a linear layer. And then it uses a local context, which is only have a kernel size of 3, which is crazy that it can mimic. Let's see. Okay, so this takes 240 seconds. 213. I would say it's probably sub-optimized because there's a for loop in here. So PyTorch not completely optimized for that. And it definitely has a different style output. It makes it more, so in the Tiny Shakespeare, they have conversations like this. So it does look, in that part it looks much better, even though, let's see, 2.8 versus 2.70, 3.05, and 3.2. So the losses look not as good, but it feels like it has better structure in it. And then last, we used, what I did was do the Kolmogorov-Arnold network, along with the Clifford net style stuff. And so that it's definitely bigger. I should have adjusted for that, but 1.3 million parameters, and it gets all the way down to 2.66 with a 3.08 validation loss. So you can use the Kolmogorov-Arnold network in here. I will say I don't think it looks as good. There's definitely, like, the words are all mostly real words, it looks like. I'm also not sure on some of these words. They might be of Old English. Not a clue. But I did think the regular Clifford net looked like the more conversational that it has. What was he? Oh yeah, I'm just gonna go through the con. So we have the Clifford net part. Let's see where the con part comes in. Because I think I tried to do the con instead of all of the linear layers, and that did not work very well. So we have the Clifford blocks. So we're going to do the embeddings, the Clifford blocks. LM head is the con linear. I don't know why it calls it con linear, but yeah, let's see here. It uses splines, looks like B splines to approximate the function. So spline order, which yeah, I don't really even understand what's up here. I don't understand this part yet. Okay, so I'll have a linear for the base. Let's see, these splines. Spline right view, spline out. Yeah, I haven't read through that part. There was a different one I read through that was, I wish I remember which one it was, but it basically used, let's see if it's over here. I think I liked this one better. So the con layer, it uses this, which is a way, I guess it's called the Chebyshev polynomials. Basically, I understood this more. It's more of a way of making polynomials. So for I in range from 2 to self to degree, let's see, what's t? T is torch one's like x norm by x, what is that? Torch one's like x. I'm assuming that's the size. Yeah, I don't remember exactly, but oh no, okay, yeah. So ones, which are the so t is equal to torch dot ones like of x norm. So this is in the shape of x norm, and these are all ones, comma. Second part of the list is x norm. So you could think of it as like this is x sum, and we need some a. Let's call the letter a, ax plus b. The ones like, we're starting out the b as ones. X norm itself is the ax. So ax plus b gets you an output. And so those are the first two parts of t. The next part, we're going to append 2 times x norm times ti minus 1. So we're on the second one. So we're kind of on sorry, not second. We're on the third one. So it's the 0th, the first power of x, the second power of x, and the third. So right now we have the first 2, 0 and 1. Then we're going to append 2 times the data itself, x norm, which is just the tangent of x, times ti minus 1. So 0, so we're on the second one, starting out 2, I minus 1 is this. So 2x norm ti minus 1, which is basically saying 2x squared. What is it? Minus ti minus 2, which would be the 0th part, which are the ones, which is going to be basically the b minus b. And then the next time through the loop, all the way up to degrees plus 1, we'll have, so the next part will be, well, okay, first of all, this all goes in this 2 spot, because that's the the polynomial degree 2, and we'll go to degree 3, which would be 2 times x norm times ti minus 1. Ti minus 1 would be this spot, which is this. So that next one would be 2 times x, and then times, let's see, times, so 2 times x times ti minus 1, so it would be this one, which is all of this, which would be 2x squared minus b, and that'll be minus ti minus 2, which would be the first one, which is x. And you continue as many degrees as you have. My number of degrees is, I think that one's set to 3. Yeah, I think it's set to 3. But yeah, so it uses, yeah, go ahead and look into Kolmogorov-Arnold networks to get a better explanation. But basically, it uses additions of different it's hard to explain. You add together different functions of each variable. You don't know how complicated those functions are. They could be extremely complicated, but you only have if you can perfectly find them, you only need 2 times the number of inputs or variables, 2 times the number of variables minus 1 of those functions, which could be many times less than a neural network, which they need for it to approximate a function. It needs, with one layer, an infinite number of neurons. But yeah, the con is a different direction, a different idea for approximating. Well, I guess not even approximating. It perfectly is functions if you find the right functions. And basically it means it decouples the data kind of into only additions, I believe. But yeah, it's complicated. I don't fully understand. I think the main way people do is using B-splines. B-splines are the better way because it gives more versions of functions. This is not as good because it limits you to polynomials, whereas B-splines can act like anything. I don't know if that's right. I think, yeah, because B-splines can split over a grid so that it can do non-polynomials, where I assume this is across the whole width of the space. I don't know, whatever. But yeah, so those are the two things I was looking at. I also looked at combining the Clifford with JEPA, and so far my findings are, I thought I wrote a note at the top, it doesn't seem as good. And I think that's, let's see. I also did a cross layer attention Clifford. I don't remember what the results of this were. I'll redo it and find out. But yeah, I will try to get back to the old videos of the two things I was working on were a transformer in C++ and doing CUDA kernels. I remember there's an article I wanted to do of sigmoid in a CUDA kernel efficiently. There's an article that goes from steps from naive to more efficient, and really good. But yeah, that's all for today.